Okay, I'm going to go over the homework for Unit 6, Section 1, Day 2. I'm going to do each problem. And this way, if you have a question about a problem, you can, fast forward to the question you have a question about, and hopefully I'll be able to answer it in this video. We're going to start with number 1. Given the feasible regions shown, what is the maximum value of the objective function c equals 2x plus 6y? Okay, we just need to take each of our intersection points and plug those into our cost, our c function here. So we have 0, 0, we have 0, 46, we have 25, 25, and we have 30, 0 as our intersection points. And if I plug in 0, 0 into this cost function, 2 times 0 plus 6 times 0 is 0. If I plug in 0 for x and 46 for y, I get 276. If I plug in 25 for x and 25 for y, I get 200. And if I plug in 30 for x and 0 for y, I get 60. So our maximum value is at 276. All right, easy enough. Let's go to number 2. We're given our objective function. We're given 4 constraints, and let's graph those constraints. So we have x is greater than or equal to 2. Oh, that was almost a big screw up. Let's go through the x value of 2. We have x is less than or equal to 5. Let's go through the x value of 5. Y is greater than or equal to 1, so that's going through the y value of 1. And y is less than or equal to 6. That's our region. We have 4 intersection points that it's going to want us to write down. We have 1 at 2, 1, 5, 1, 5, 6, and 2, 6. And, you want to plug each of those in to this cost function and see which one gives you the right answer. And I'm going to tell you right now, at 5, 6, I get the 29, which is our maximum value, and at 2, 1, I get 6, and that's our minimum value. All right, we got number 3. This is our objective function. These are our 4 constraints. The x is greater than or equal to 0, and y is greater than or equal to 0. Those are easy to graph. That's x is greater than or equal to 0. That's y is greater than or equal to 0. These guys right here, you're going to need to put into y equals mx plus b form. If I change this one, you should get y is less than or equal to negative x over 2, or negative 1/2 x, plus 14. Oh, no, sorry, plus 7. And for this guy, if I subtract over the x and then divide by a negative 1, don't forget to flip your inequality. You should get y is greater than or equal to positive x plus 1. The signs changed as we got rid of the negative. If I graph this first guy, y-intercept is 7, down 1 over 2, down 1 over 2. He kind of goes off the page. If I graph this guy, y is greater than or equal to x plus 1. Get this, and this one's kind of funky. We don't have 2 enclosed regions because we stopped this graph here, but if we had kept this going, it would look like we had 2 possible enclosed regions. If that ever happens, you just need to think carefully about which region, contains all these inequalities correctly. What I mean by that is, this guy right here is all the space that is, x value is greater than 0, so this line right here going this way, all y values greater than 0, this line right here going this way, and then all y values less than the negative 1/2 plus 7, that's the shaded region below this line, so that's this right here. And then this last guy, y value is greater than or equal to x plus 1, well, here's x plus 1, and if it's greater than, it needs to be all the values above it. So it couldn't be this guy down here because he does not satisfy this last equation, y value is greater than or equal to x plus 1. All right, we have 3 intersection points. We have one at 0, 1, 0, 7, and 4, 5. You want to plug each of these in to your cost function, and what you should get for your maximum value, that should occur at 4, 5, and I got 18 for that. And for your minimum value, that's going to be 0, 1, and I got 2 for that. Okay, flip over. All right, this is just sort of more of the same here, more practice. So I'm going to graph these functions. Before I do, I'm going to go ahead and put this into standard form and this one into standard form. My standard form for this guy is y values less than or equal to negative x plus 7. And my standard form for this guy is y values less than or equal to negative 2x plus 10. Hopefully y'all agree. If I graph the x is greater than or equal to 0 line, the y is greater than or equal to 0 line. For this guy, our y-intercept is 7, slope of down 1 over 1. For this guy, oh, sorry guys. For this guy right here, negative 2x plus 10, we have a y-intercept of 10. And he's going down to over 1. And so our intersection point, our feasible region, is this guy right here. We have 4 intersection points. The origin, 3, 4, 0, 7, and 5, 0. And you just want to take each of these and plug them in to your objective function. It looks like our maximum value is going to occur at the 0, 7 point. When we do that, we get a value of 7. And it looks like our minimum value is going to occur at the 5, 0 point. That's going to give us a minimum value of negative 10. All right, see if I can keep this one on the page. Number 5. This one's a lot nicer to do than number 4. These two guys are already nice, and the x plus y is less than or equal to 4. So you need to subtract over the x for that. So we're going to have our x is greater than or equal to 0 line, our y is greater than or equal to 0 line, and then the negative x plus 4, that's a y-intercept of 4 and a slope of down 1 over 1. We only have 3 intersection points on this one, 0, 0, 4, 0, and 0, 4. And it looks like our maximum is going to occur at 4, 0. That gives us a maximum value of 20. And our minimum value is going to occur at 0, 0. That gives us a minimum value of 0. All right, and then the last one here on this page, we have this objective function, and then we have 5 constraints. How annoying. You're going to want to put these in standard form. I'll sort of show you what I got. This one ends up being y values greater than or equal to x. This one ends up being y values greater than or equal to negative 3x plus 4. And this last one's the only one that takes some real work. It's going to be y is less than or equal to negative 4/5 x plus 9. All right, we got to graph all 5 of these. We got the 2 easy ones. X is greater than or equal to 0. Y is greater than or equal to 0. Y is greater than or equal to x. That is a y-intercept of 0, and it's up 1 over 1. Negative 3x plus 4. Y-intercept of 4 down 3 over 1. Down, I guess that's all we can do with that. And then the negative 4/5 x plus 9, a y-intercept of 9, and then down 4 over 5. Oh, it intersects nicely. Down 4 over 5. All right. So the region that is enclosed by sort of all the graphs, all the inequalities, except for this, I guess this y greater than or equal to 0, he doesn't really factor in again. It's this right here. You know, if you're having a hard time finding which one actually is supposed to be your region, because we kind of have another enclosed region here, and sort of one here as well. Again, think about the inequalities. Y value is greater than or equal to x. That was this line, so it's got to be the region above it. Y value is greater than or equal to negative 3x plus 4. That was this line. It's got to be the region above that. And this last one, less than or equal that was this line. That's going to be the values below it. And so this region satisfies all three of those inequalities. These other regions don't satisfy one, like at least one of these inequalities. All right, our intersection points. It looks like we got one at 0, 9, 5, 5, 0, 4, and 1, 1. And this is one where I tried to just sort of look and guess the first time around, and that kind of messed me up. So I would make sure you're actually trying all four of these points for your max and your min. For my max, at 5, 5, I get 65. And at 0, 4 is where I got my minimum of 12. So not 1, 1. If I plug in 1, 1, I get 13, and that's bigger than 12. All right, if you flip over, we got two more sort of problems. All right, so number 7, we have sort of two nice and easy ones. This one's not so nice right now. I would need to put this in standard form. If I subtract over the 2x, divide by 3, I'm going to get y is, why did I have it like that? Y is greater than or equal to negative 2 over 3x plus 6. And then for this guy right here, if I add over the 30 and divide by 3, I get y is less than or equal to 2/3 x. Minus 10, or plus 10. Oh, I know what the problem was. This sign should have been flipped to start with, or else this problem doesn't make any sense. So go ahead and flip that. Most of y'all probably wouldn't have noticed, but it's going to give you a nice region to work with without you having to figure it out, but it should be less than or equal to there. All right. So if I graph these, the negative 9, x values less than or equal to negative 9, that's the straight vertical line right here. The y value is less than or equal to negative 2/3 x plus 6, so I got my y-intercept of 6. We're going down 2 over 3, down 2 over 3, over 3. Let's see here. Y is greater than or equal to 0. That is the straight horizontal line down here. And then the 2/3 x plus 10, y-intercept of 10. We can't really go anywhere to the right, but we can go the other direction down to left 3. We get a nice intersection point. All right, so the region enclosed by this line, this line, this line, and this line. That's that whole region right there. That's our feasible region. We have 4 intersection points, negative 9, 0, negative 9, 4, negative 3, 8, and 9, 0. Our max and our min, I would recommend plugging, trying all 4 of these points. I get a maximum at 9, 0. If I plug in 9 for x and 0 for y, I get 36. And I get a minimum at negative 9, 0. If I plug in negative 9 for x and 0 for y, I get negative 36. All right, we got one more. It's a word problem. We got a bakery going on here, making 2 types of cakes, chocolate and vanilla. Apparently, there's some issues with the oven. It gives you all this information. You can read it over. And it go ahead and builds our constraints for us. So we're going to jump right in here. So we're trying to maximize the amount of cake, like our cakes we can make, or maximize our profit. And we have these constraints here. So x is greater than or equal to 0. Y is greater than or equal to 0. X is less than or equal to 8. This guy's not in a nice form for us. I need to subtract over the x. So we got our 15 down 1 over 1. Careful with the rectangle square, like the coordinate squares here. They're rectangles. Sure you're following those. Down 1 over 1. And then y value is less than or equal to 2x. Y-intercept of 0, and then sort of up 2 over 1, up 2 over 1. region. Let's sort of follow these. Again, we have 3 regions here. So which one are we talking about? All right, you're going to want to look at sort of the funkier ones to sort of help you out with that. So the y value is less than or equal to negative x plus 15. That's this guy. If its y value is less than that, we want the region below that. So this one's not going to be our region. It's either going to be this or this. And then y value is less than or equal to 2x. Well, that's this line. If it's y is less than, it's going to be the area below that. So it's not going to be this one. So if it's not this one or this one, it's going to be this guy right here. All right, our intersection points occur at 0, 0, 5, 10, 8, 7, and 8, 0. Where it's only asking us for our maximum, so you want to take each of our 4 points and plug these in and see which one gives you the best answer. And don't get tricked. I thought it was 8, 7. I thought it was going to be 8, 7 for sure, but it's not. If I plug in 8, 7, I get 37. But if I plug in 5, 10, I don't know why that one didn't look good to me. I get 40. So that's our maximum. How many chocolate cakes then? Well, the x value represents chocolate cakes, and the y value represented vanilla cakes. It says it right here. All right, that's it for the classwork. Hopefully, if you had questions, me working these out helped you out. If not, please email me and ask your question. And don't forget to go online and do your daily quiz for today.